Now at this point, I'm going to make a variable change. Okay, so I'm going to define k minus 1 as I. And the range of k in this sum, you see k from 1 to n, and that means I will range from 0 to n minus 1. Okay, so that will be n minus 1 choose k minus 1. It's going to become n minus 1 choose I, right, per my definition. And p to power k minus 1 will be p to the power I, and this will be 1 minus p to power n minus 1 minus I, because n minus k is um, n minus 1 minus k minus 1, and this is I. Okay, and of course the summation limits is from 0 up to n minus 1 in this case. Right, now at this point you have to recognize this as a PMF. N minus 1 choose I, p to the power I, 1 minus p to the power n minus 1 minus I. Okay, this is the PMF of binomial with the parameters not n and p, but with n minus 1 and p. Okay, it's the number of successes in n minus 1 independent Bernoulli p trials. Okay, n minus 1 choose I, p to the power I, and 1 minus p to power again n minus 1 minus I. This is the PMF, and I sum this from I equals 0 to n minus 1. So that is the entire sample space from 0 up to n minus 1, right? So I'm summing up the PMF of y, a different random variable, let's say. It's binomial, but with parameters not np, but n minus 1 and p, okay? Which should be what? 1, because the sum of the PMF, okay, all probabilities, so it makes 1, and the result is found as n times p. So this shows you to be aware of the relations or the parameters of the distribution. And at this point, for instance, you should actually, when you look at this, you have to realize this is a binomial distribution with parameters n minus 1 and p. Okay, so be careful about what distribution you are working with and what parameters are involved in this distribution, let's say. Okay, so the result is expected value of the binomial with n parameters n and p is n times p. Okay, so in this case, for instance, expected value of y would be n minus 1 times p. Okay, and next, let's look at the second moment of binomial distribution. And here again, I have the PMF here, but here I have k square, obviously. And the sum again starts from 0 and goes up to n. Again, I realize that I do not need k equals 0 in the sum because the term will be 0, so I can start it from 1. And again, I can cancel out one of the k's in k square with the k term here. So that will become again k minus 1 factorial. And I'm going to pull out this n, and therefore this n factorial will become n minus 1 factorial. And again, I'm going to pull out 1p, so this will be p to the power k minus 1, times I have 1 minus p to power n minus k. Okay, so what now? Again, here I have n minus 1 choose k minus 1, right? This term here is n minus 1 choose k minus 1. In the expected value computation, we did not have the k here. Now we do have the k. But when you make the variable change from k minus 1 to I, okay, I will have again the range of the summation from 0 to n minus 1. Sorry, this should be n minus 1. Okay. And then I have again here n minus 1, choose I, p to the power I, 1 minus p to the power n minus 1 minus I. Okay. And again, similarly, I should have n minus 1 here, n minus 1 here. But what is this? Now here you see I have one I here and 1. I plus 1 times this. So I actually separate it into 2. So in this sum, all the summation range is the same. I times n minus 1 choose I, p to power I, 1 minus p to power n minus 1 minus I, this. And due to this plus 1, I have another term here. And n minus 1 choose I, p to power I, 1 minus p to power n minus 1 minus I. Okay, so what are these? You have to recognize this as the expected value of this binomial distribution, again with the parameter n minus 1 and p. Okay, since I have an I here and the range is from 0 to n minus 1, it's the entire sample space. So this is the expected value of y. So that was n minus 1 times p, if you remember. And this one is the sum of the PMF. So this term here is 1 actually, this here. Okay, so that is 1. If, sorry, we are looking here. So this is the expected value of the binomial distribution with n minus 1 and p, and plus I have this term as 1 here. So this is the second moment, and you subtract the square of the first moment, which is n square p square. From this, you get the variance as n times p times 1 minus p.